Every powerful language model today is built on a mountain of human text, scraped from the web, cleaned, and fed in by the trillion. But high-quality text is running out, it's full of human bias, and it's expensive to curate. So here's a wild question this paper asks. What if a model could learn to reason, not from language at all, but from watching tiny colorful grids evolve? The idea is this. Before showing the model any language, you warm it up on synthetic data generated by neural cellular automata, little cellular grids with their own rules. They call this extra stage pre-training. And astonishingly, a model warmed up on these abstract grids learns language faster and better than one warmed up on real text. Let's frame the core hypothesis because it's beautiful. The authors argue that what makes language such good training data isn't its meaning, it's its structure. The long-range dependencies, the hidden rules, the patterns. If that's true, then any data with rich structure should teach a model to reason, even if it contains no words at all. And the results back it up. Warming up on just 164 million tokens of these synthetic grids improves downstream language modeling by up to 6%, and makes the model converge up to 1.6 times faster. The kicker, this beats warming up on 1.6 billion tokens of real web text, 10 times more data, with more compute. And it's not just about predicting text. These gains carry over to real reasoning tests, grade school math, coding, and a suite of logic benchmarks. Before we dig into the results, though, let's understand the strange and clever method that makes this work. So what exactly is a neural cellular automaton, and how do you turn one into training data for a language model? Let's build it up piece by piece. Start with a grid of cells, here 12 by 12, where each cell holds one of 10 colors. At every time step, each cell looks at its immediate neighbors, its little 3 by 3 patch, and updates its own color. If you know Conway's game of life, it's the same idea, a simple local rule applied everywhere at once. Here's the neural twist. Instead of a fixed hand-designed rule, the update rule is a small neural network. In the magic move, they don't train that network at all. They just fill it with random weights. Every random network is a brand new universe with its own physics, so a single generator produces endless, wildly different worlds for free. But random universes range from boring to chaotic, some freeze instantly, others are pure noise. Authors needed a way to pick the interesting ones in the middle. Their trick is delightfully simple. They compress each grid sequence with gzip, the same tool that zips your files. How well it compresses is a cheap, practical proxy for how complex the dynamics are. Now you turn these grids into something a language model can read. They chop each grid into little 2 by 2 patches, give each patch a token, like a word, and lay the time steps out in sequence. The result looks just like a stream of text, except every token is a piece of an evolving grid. And here's why this teaches reasoning. Each sequence comes from one hidden rule that the model has never seen. To predict the next patch, the model can't memorize, it has to figure out the rule from context, then apply it. That's exactly in-context learning, the same skill that powers language models. NCA is a pure gym for it. Putting it together, training has 3 stages. Stage 1, pre-training on the synthetic grids, that's the new idea. Stage 2, normal pre-training on real language. Stage 3, fine-tuning for a task. They transfer all the model's weights from stage 1 into stage 2, accept the word embeddings, and measure what carries over. That's the whole recipe. Random grids, filtered by compressibility, tokenized, and used to warm up the model before language. Now, does this strange curriculum actually help? Let's look at the numbers. Across model sizes and random seeds, the NCA-warmed models beat every baseline. Training from scratch, warming up on the DIC formal language, and warming up on real text. The smaller 400 million model improved by 8.6%, the larger 1.6 billion model by 5.7%. Consistent and robust. Now the most surprising result in the paper. Pitted 160 million tokens of synthetic grids against 1.6 billion tokens of real text, 10 times more data and more compute. The grid still won, 5% better perplexity and 1.4 times faster. Abstract dynamics transferred to language better than language itself. And these gains aren't just about predicting tokens, they show up in real reasoning. On grade school math, on coding, and especially on the BigBench logic suite, where the NCA model hit 36.5% versus 25.9% for Scratch, when allowed a few attempts. The structure it learned from grids genuinely transfers to math, logic, and code. So what exactly carries over? They ran a clever test. After the warm-up, they wiped different parts of the model and remeasured. Wiping the attention layers hurt the most, by far. Attention is where the transferable magic lives, the circuits for tracking long-range dependencies and learning in context. There's one more elegant finding. The best grid complexity depends on the target. Code, which is rigid and repetitive, transfers best from simpler grids. Web text and math, which are richer, want more complex ones. And this matches the intrinsic complexity of each domain. The takeaway: match the complexity of your synthetic data to the domain you care about. But why would grids beat text? 2 reasons. First, with only a small budget, real text mostly teaches shallow surface patterns. The deep stuff comes much later. Grids skip straight to the deep skill, infer the hidden rule. Second, every grid sequence is a genuinely new rule, so the model can't memorize, it's forced to learn a general mechanism. Step back, and the implication is big. The model can learn reusable, reasoning-related skills from data with zero language in it, just structure. That gives us a brand new knob. Instead of scraping ever more text, we can design synthetic data, tuned in complexity, to teach exactly the skills a domain needs. Better data, not just more data. The authors are careful, though. This is a warm-up stage, not yet a full replacement for language pre-training, and the biggest grids show diminishing returns past a point. Gzip and alphabet size are just 2 crude lenses on complexity. There are surely better ones. The real open problem: how to design synthetic generators that match any target domain. So here's the one-line takeaway. A language model doesn't need language to start learning how to think. Feed it tiny grids ruled by random physics, and it picks up the deep machinery of reasoning, then carries that machinery straight into math, code, and language. The question is no longer whether synthetic data can work, but how to design it. Thanks for watching.